Okay, so we're back. Do you mind real quick put pluses if you still can hear me in the conversation? Okay, great. So it works. The first recording went well, so we have actually the working software for the recording, so that's cool. Now I launched the second recording for the second part. Okay, and I'm gonna start sharing my screen. Okay, so we're back to where we left almost, except for this thing that I added recently. So it's another example of a sum, so we're gonna do the same. I open the conversation thing and it doesn't show. Why is it not showing? Oh, shows. Great. So now what I'm gonna ask you is what's gonna be the next term for this sum. So we're here on my notebook on the right side of your screen, and the first term I already wrote, so be careful. Here we started with 1. It also can happen, not necessarily we're starting with 0. So what's gonna be the second? Okay, yeah, it's more precisely 2 times, oh wow, my French keyboard, 2, oh, I'm gonna do this, times, and in the parentheses 7, perfect, thank you very much. So it's gonna be 2 plus 5. Okay, that's gonna be 14. Great, thank you very much. So we are not gonna write it until the end of times. But the last sum that I wrote has actually only 4 terms, so that we're able to write down. So let's go. First term will be easy, 0. Cool. Then the second, 2. Cool. Then the third, I agree with 8 because I takes value of 2. So we have 2 times 2 to the power of 2, 2 times 4, 8. And the very last one where I takes value of 3. Yes. Okay, great. Thank you very much. So that's how the sums work. Again, you got it. And for the identities also it was all good. Now let's move to our useful formulas. Okay, so here, you really don't need to learn them by heart. And you're most likely not going to use like formulas the way they are written here during the PSME, but you might need them, start needing them for the M2 for the same thing of summing up consumers. So sometimes we need these formulas to then multiply this by our utility function. You'll see. So anyways, this now is gonna be just an exercise for you to, remember of how to multiply and all that. So here for the just I, we have this formula. How did we get it? That's pretty easy actually. So we just wrote all our terms, and this is the classic standard arithmetic progression 1, 0, 1, 2, 3, 4, 5, 6, 7. So this is a sum of an arithmetic progression, what you have here, with the first term 0 and the second term n. Okay, great. Then I squared. So given you have this form and I takes different values from 0 to n, this is what you're gonna get in the end. It's pretty big, ugly, but at least we have a formula. Then to make a sum of cube, we have a bit prettier formula, still not super great. Then we have this binomial theorem, which, yeah, honestly, you're not gonna use it this year, but nice to recall what this is all about, also to get in the math mood. And well, now, no, I'm not gonna ask that. I'm gonna ask, put please a plus in the conversation, given you really don't understand what this binomial theorem is about. Like you see it, but you have no idea and you've never seen it. That's a good question. So given you've never seen it, put a plus. Okay, cool, cool. Thank you. Great. I think what I need to explain here is this weird notation of n over 1 in a big parenthesis. Okay, pretty bunch of people. Okay. Okay. So what that means first, and how this binomial theorem works and where it came from, that is going to be useful. Just understanding how this works. So first I'm gonna start with an example. A plus b to the power of 2. Well, that you've seen, and you know that it is equal to a to the power of 2 plus 2ab plus b to the power of 2. Well, this is an example of Newton binomial. So in this case, we have 2 as a power. So you remember this formula. You also might remember a formula of cube, but for sure you don't remember a formula of fourth power. So that's what I'm gonna show you. Let's take x and y, because in the slides we have x and y, x plus y to the power of 4. Okay. This is the right part on my slides. You can see this. Right part. Left part is the weird looking sum. So, what is n over I? This is used in combinatorics, in statistics. How many times can we create? Oh, yeah, that's a good question. Someone who didn't put plus and already saw this thing at least once. What do we calculate this way? N over I, well, it's not over, like Ni in parentheses. Just try to write the way you understand it, like what can we calculate with this, regardless binomial theorem, just this, maybe you don't know how to expand it. Combination, yay. By combination of what? A number of times, I think, happen in a range of time, for example. Okay, yeah. Combination, that was good. A number of times, I think, happen is good. Pretty much we have n numbers, right? How do I take things from perfect? Yeah, well, that's the best explanation. The number of combinations that I can write if I have, for example, n letters and I only use I. letters. Well, we can take a example with numbers. So let's say n is equal to 6, I is equal to 3. So I have 6 letters, and what I want to know is how many combinations of 3 I can construct out of that. And that is used in probability theory, obviously, because then you can divide it to you can divide certain combination to a number, to the total number of combinations, and get the probability of getting this exact combination. Okay, so let's take a quick look of how to expand this thing, and I hope now this is going to work. We're gonna need left, then we're gonna need n I, and then we're gonna use the right. Yeah, didn't work, whatever. So this is how I'm gonna write it in these notes. So you can now use your notebook that you prepared, as I asked. How to calculate this? So fraction, I know how to write fraction. So here we're gonna have n factorial over I factorial times n minus I factorial. Okay, so you see this ni is the same as this ni from here. Great, so what is a factorial? Good question. Now, for n factorial, that will be, that I'm gonna write here, n factorial equals to 1 times 2 times 3 times blah 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 blah. So we take all the numbers until times n. Okay, so now we have all these formulas. If you're lost, for example, right now, or you hate the way I explain, you can write something like a question in a conversation. I'm checking it. Okay, so this is the factorial, how we calculate factorial. Now you can see that this n over I, that's how I'm gonna call it, is n factorial, so the product of everything until n over I factorial, so the product of everything until I, and blah blah. Okay, great. So now we can expand x plus y to the power of 4 using this formula. Now we have all our instruments here and all our formulas here. Oh, in the PDF that I'm gonna prepare, I'm gonna try to fix this so for it to look actually pretty. Let's go to the example. So in our example, n is 4. Okay, so here in this sum, we will have 4. Here we will have 4. Here we will have changing variable, I, taking all values from 0 to 4. Here we're going to have 4, and again our I. Okay, great. So, well, I'm going to write it, and then you're going to put pluses given you agree with me. For now, I don't have any messages in the conversation. Okay, so the first combination, right, will be n over 0. Here, what I'm gonna tell you, you most likely also remember this. 0 factorial is equal to, write it to me in the conversation. What is 0 factorial equal to? 1. Why? Because this is a convention. For now, that's all you have to know. Great. So eventually what we're gonna have here as a first element, first term, So we have, in this case, right, we have a coefficient that is calculated according to the formula. Then we have our variable x to the power, and then our variable y to the power. So next question to you is, what's going to be the first coefficient? So the first term, how do we write it? You can write the whole first term if you want, or just a coefficient, because the coefficient is the most difficult. X to the power 4? Okay, yeah, you got it. The coefficient will be 1, calculated according to our combination formula. So we get x to the power of 4. Okay, now I see that you can help me with the next one, some of you. So go ahead. Next will be calculated as the combination of n over 1 of 4 over 1. Any other ideas? 4 over 1 will be, yeah, okay. So the way we do 4 over 1 is we do 4 factorial. Oh, yeah. 4 factorial over 1 factorial, which is going to be 1, over 3 factorial. And here just, I'm going to show you how beautiful it is. Cannot stop admiring this thing. 1 times 2 times 3 times 4. So now you might think, well, this online thing actually is not as great, but at least you see everything that I write, because on the whiteboard maybe my handwriting is not understandable. So here it's slower, but it's clearer, let's say. Okay, so our 3 factorial comes to this. 1 I'm not gonna even write, so we can simplify it and get just 4. And that's the result that we're gonna get here. It will be 4 x to the power of 3, because it was 4 minus 1, y to the power of nothing, to the power of 1, because our I is now taking the 1 value. Okay, great. Let's move on. What's going to be the next coefficient? It's going to be a combination 4 over 2. Yes. Well, with the coefficients, it's pretty easy. I mean, with the powers, exponents, it's pretty easy. You just do 4 minus 2 and 2. And for the coefficient, if you don't know how 6 was obtained here, I'm going to show the last time. So we do 4 over 4 factorial over 2 factorial times 2 factorial. And what we get is another fraction. So here we have everything. I'm not gonna write times. Okay, 1, 2, 3, 4. And here we have 1, 2, 1, 2. So then, maybe I can, nah. How do I just put a star? Yeah, you still didn't get used to French keyboard. So we do 1, 2, we can simplify. And then what we get is, in the very end, 3 times 2, because that's how we simplified 4 and 2 times 2, and it is 6. Okay, great. So that's how we got 6 as a coefficient. X squared, y squared. Then the next term is going to be, yes, that's lucky. Now it's doing a mirror thingy. So we have 4x y to the power of 3. And then we have the last one, which is, yes, y to the power of 4. That actually fit all this expression in my... I can do like this. That is better. Okay, perfect. So that's how binomial works. If you've never seen the formula, for sure you've seen this, and then for sure you've seen a cube, and now you understand how the fourth power works. Again, this is more for your for the fun of it, right? Nobody is going to ask you learn this formula by heart and know how to use it during the PSME, for sure. Then M2, don't know. All right, and then a couple of other formulas that you can see here. This is the sum of the exponent, which is actually not that useless, because you might have this expression of exponent to the power of changing power. Well, the example, I want to have an example of the same of consumers, but well, you'll see that. Again, no need to learn it by heart. And the last formula is, okay, you should know what this formula is about. The last one with infinite. Does it look like something you've seen or you've known? Exactly. This is something that you learned at school. It's geometric progression. And well, given that geometric progression has a coefficient of like 2, we're not gonna get anywhere, because it's gonna be increasing infinitely. But in this case, this part is important, that r is less than 1. So the absolute value of r is less than 1. Given we have a fraction there, we can use this formula to get an approximation after all, but a value, so a number, even if we have infinite number of terms here. Okay, that formula you're gonna need, so worth noting. Okay, and now you're on your own, so it's gonna be a bit tricky because I have the solutions, but they're super long. So most likely, for example, for the third, I'm gonna just give you the answer and you're gonna compare with your idea, and we'll see if it works. And if it doesn't work, I'll invite you to try on your own and get this answer. And given you don't get it, I send you the solution, no problem. Okay, so now with this exercises block, every time we have it during our class, I'm gonna give you 5 minutes. So now it's, okay, exactly at 4 Paris time. We're gonna check the answers, and here you go. Use your notebooks and have fun. This is very weird. I don't see you. I don't see that you're working. Yeah, if now, for example, you don't like, don't understand, don't feel comfortable with this format, don't give up. We still have the second week offline, and I know for a fact that that works. So I know you're for sure not enjoying this role of being a test rats for our first online math refresher, but we all do our best. So, and you all have my email to ask me questions anytime. Just make sure you mark what you want to ask me. Okay, not a big deal if you didn't manage to solve all of them by now. It's okay. Let's just go through the first ones. First one is easy. because we've done it already. Oh, the goal was to reach, oh, sorry. Now you can write me on the, again, on the conversation, the sum of the very first one, so the answer to the very first. Okay, cool. It's 101. It's like the same as we've done with A in the, yeah. So this is the same as this. We can use this as a formula, but well, it's not very much of a formula after all. Okay, great. So that is 101. Perfect. I see you got it. Next one, you were supposed to use a formula, and what did you get? 1/3. I got different. 4/3. That's what I got. So here I'm not gonna write anything or explain anything because this is the formula, right? So you might have just miscalculated, or arithmetics is the worst for everybody. But well, it's 4/3, and I approve the last answer in our conversation. Now the third one. So what happened here and what I wanted you to do? So I wanted you to use first of all identities and second of all formulas. So let's see. I'm gonna write the answer, and whoever got this answer is going to write plus in our conversation. Now you got this instrument very well. So, and given nobody got it, I can explain. Well, at least something. This is the very, very, very final, right? So maybe you didn't get there. It's okay, but just look at it and think, were you getting there? Or is it something, oh, sorry, minus. Something that resembles a little bit your calculations? Okay, I got 1 plus. Somebody else? Well, you might have just been in the beginning of a very long expression, and there was a sum of, actually not a sum, the difference of 3 members, and then you were supposed to make a sum, and the common denominator would be 6. No? Not recognizing? Alright, well, again, this is more of math for fun stuff. So if you didn't get anything, don't worry. I'm gonna just explain the principle, right? Not the whole arithmetics. You get there, obviously. You know how to deal with fractions. Just what I wanted to see. So first, what I wanted to see is you expanding this. So now we have a product, and given you expand it, so multiply everything by everything, you'd get I0 to n. So here you will get something like parentheses, so just multiply blah 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 blah, and that would be I squared plus minus I minus 2. Okay, that's what you get. And from here, I wanted you to use this identity, so the sum of different sums can be decomposed to 3 sums. So you were supposed to get 3 sums here. Not gonna write it. No, I'm gonna write it. Well, sum without limits, okay? So it will be 2 minus, no, minus another sum of just what we have here, I, minus another sum of just 2. So with the last one, for sure you know how to deal, because that's our first exercise here of 1. So here you have 2, and that would be 2 times n plus 1, this one. And here, for these first 2, you have formulas. So that's how you decompose them, used formulas, and just got a huge expression, very ugly, that eventually comes to a nice thing like that. I tried to make it pretty, so I think it's pretty. Great. So then what we had this sweet expression, and wait a second, I lost my conversation and I have one new message there. No, it's not a plus b to the power of 6, because what we're missing here is the coefficients, right? So it's not, we don't start with 6, well, that would be 1. In here, the coefficient was supposed to be 6, given it was a binomial theorem, but we don't have coefficients. Yep, that's good. Well, not exactly good, because you have n, Lucas, that is not changing for a, but a's power is also changing. So I'm gonna write this very beautifully. We are gonna have, first of all, here what matters is the limits. So it was a sum from I equals 0 to 6. That's the first thing to determine. And then we have a to the power of n minus, okay, here we go, into the power of n minus sorry yeah, well, I was thinking to choose LaTeX, but in LaTeX it will take a lot of time compiling, so would make sense. n minus 1 minus 5. Oh. No, not even that. Sorry. So here we have n, then minus I. Okay, I keep it like that. I'm sorry for this ugly thing. So this is supposed to be n minus I, I'll fix it. B to the power of I. Okay, so here you see that it is almost the same as our binomial theorem, except the coefficient is not there. So nothing, absolutely useless. It's not a formula, it's nothing, it's just an exercise. Okay, great. So again, you didn't get it and you want to get it, you can contact me or rewatch again our recording that is actually happening. Great. And we move on. So before we switch to product operator, we're gonna go very fast through that. I'm gonna show you something that is very, very, very useful. So I started saying that there is this thing of sum of consumers, but most likely you didn't even see that. So you understand that yes, given we have a country, a state, and we have a bunch of consumers that are identical, homogeneous. That's our usual assumption in economic growth and in macro. So to calculate the common utility, the social utility, we need a sum. But what you most likely have seen instead of using sums is integral. So here on my right side, on your right side of the screen, what I tried to show is the transition from the sum to the integral. So first, it's just so you don't get scared when you see this in economic growth. So the idea of sum is pretty clear. We sum up consumers. So where does this integral come from? That's pretty simple. So integral is what by its nature? It's an area under the curve, right? So using the integral, so using this left part, what we calculate is actually the area very, very, very close to the area. It's still gonna be, well, that's how we have this equal but not equal. Anyways, integral is the area under the curve from A to B, and the curve, this curve, is just a plot of a certain function f. So by taking integral, we calculate the area under the curve. It's not an indefinite integral, it has its bounds. And then with the sum, you can see what is written here, that this is a sum of little squares, so the smaller the squares get, the closer we get to the actual area under the curve. And we take every value of x, like for x, of every value of the function for each x, we have kind of like pillars like that, like on this picture. And it is actually approximately equal to this integral. And what you're gonna see through the majority of growth and macro is not the sum, it's an integral. So try to, well, understand, or the worst case memorize, that this is the same thing. And why do we call it left Riemann sum? Well, first of all, Bernhard Riemann was the first person to define the integral the way we know it now. Left, you can see it's because here we start from the left. So left corner of our pillars touching the curve. We can have the right one and it's a bit different. Well, it doesn't matter actually. If you've never seen Riemann integrals, don't know what it is, don't worry about it. Just remember from here that the sum can be approximated by an integral, given we are in a case of continuous functions. And most likely for all the utility functions you're gonna see, except for micro, you're gonna be in the case of continuous functions. Okay, perfect, great. So again, the PDF of all these, including this, I'm gonna upload. So I'm gonna download and then send to you. So that's okay. Don't worry, you'll have time to look through it again. Okay, cool. No. Okay, I'm gonna switch to slides for a second and deal with this. Product operator, don't wanna even spend too much time here because you're really not gonna use it. But, well, you can tell me where technically this thing can be used. So, just write me the ideas of how can we use product operator, well, in economics or statistics. Okay, so we can use them obviously many ways. Logarithm functions, yes, and the simpler in probability theory. For example, we need to calculate the probability Yeah, in factorials too. Yeah, that's pretty much the definition. Maximum likelihood, perfect. That is one way to use it, and you're going to see it, I think, in econometrics. And well, before maximum likelihood, what the simplest answer that I thought of is when we calculate the probability of a joint event. So we know that if A happens at the same time as B, the probability of them happening together is the probability of A times the probability of B. So here we go, we have a product. And with this logic, we create the maximum likelihood method. So we create a function of a product and then we maximize it. Okay, great. So what you have to know about products is that given we start with 0, we get 0. Because the first term being 0, we can multiply it by whatever we want. And here, as an exercise, what I ask you to do is write n factorial with the help of the product operator, where, so what I meant here is that I want you to write it with the limit, the lower limit 1, and with the lower limit 0. So with lower limit 1 is very simple. And with the product limit 0 is also not that difficult. Just 2 seconds, so I catch up on my notes, and you can write it on your notebooks. Okay, so with 1, I'm sure you know how to do it. And with 0, so I equals 0 to n, right? And we have our I plus 1 just to fix the 0 thingy. Since we start with 0, given we just write it as a product, we're gonna end up with 0 and get stuck, but to fix it, we just need to add 1. Pretty simple. So where do we use products? We already know. We use them in probability theory, in econometrics, when we need the maximum likelihood method. Okay, great. So another example that I wanted to show you, and let's see. Yeah, I can show you of a product. That's going to be, again, an exercise in math. So we take I from 1 to n, and here we have a to the power of I. So what is this going to be equal to? And it's going to be equal to something that you can write in the chat. So whenever you get it, do it. Or just the ideas. Yeah, the first answer is technically more correct, but I understand that Sarkan, what you meant is the same, just missed the parentheses. Okay, let's put it on our Blackboard too. Okay, here we go. No, actually, this time I managed. N1 plus n over n over 2, blah. So whoever got the answer obviously knows how to deal with exponents, so that's going to be our next slide. I really hope that the next part will be really easy for you because that's high school. And I still have to go through it because I need to make sure that it's actually easy for you. So don't get too bored. These are the basic rules of dealing with exponents. So we know all that. I just wrote it here for you, peace of mind that you know that you have one PDF with all the formulas combined, and you can go there anytime, whenever you need to, real quick check something. So I think there are no typos, but this can always happen, so you should be very careful whenever you check my presentations. Well, this is already student proof because last year we used that, and I think I fixed all the typos, but again, things happen. All right, so the rules, easy peasy, you understand. Then here I wrote the weird phrase, the same applies in case we have a variable as an exponent. What I meant that in this first part, I considered x as something that can change, so a variable, and the exponents, so the powers, as constants, right? So that's how we deal with that. Like, for example, let's take something x to the power, oh, I'm out of my math. X to the power of 2 times x to the power of 3. Yeah, obviously, you know that it's gonna be x to the power of 5. Great, perfect, thank you. And then what I meant, the same applies in case we have variables. So given 2 and 3 are not fixed numbers but just something as t, in case of this function, the same rules apply. So this is like that anytime. So now on this slide it's all letters, so doesn't matter, but you get it. So what is this function? Tell me. Yeah, it is time discounted utility. Perfect. And we have our minus, what is this letter? Rho, right? Minus rho as a discounting factor. This is the function that you're going to meet again, both in macro and in economic growth. You're not going to have to take an integral. You're just going to have to check it. And this is another proof of my Riemann sum argument. So this is the function that you're going to see, not the sum operator here. It's going to be integral operator. Okay, but well, anyways, you know how to deal with sums. You will not have to integrate anything, but that given you need it in the during your second year, you know what integration is anyways, I'm sure of that. Great, so here we have an exponent, right, in this utility function. So this is how we discount our utility. This is not, no, it's nothing. It's not constant elasticity, it's another one. Great, so this is an exponent plot that I put here for you just to recall it again, because we sometimes get confused between exponent and logarithm. But so this is how we start towards exponent. That's going to be the plot. You're going to use it and you're going to need it. Very, very, very nice exercises for you to relax and recall sweet times of your high school. And here, let's see how we can do it. because I want you to give me the answers. Yeah, okay. So for all that, how much time you might need? I give you another 5 minutes. And I'm gonna check the camera. Okay, go ahead, and then we're gonna just check the powers, and all this is easy, and you can find, you can type the answers in the conversation when I ask you. Okay, go ahead. Okay, thanks to the cameras that some of you have, and I'm very glad. I can see that some of you already finished, some of you still in the middle. But let's just do the quick checkup. Again, well, according to the test, you are super duper diverse group. So some of you actually might find this challenging, some of you might find this super boring. Again, it's all good, so that's why we're doing this math refresher. And if you didn't have time to finish it all now and have troubles understanding, email me. I'm gonna say it again and again and again. Okay, I have a question from Anthony. Solve all of them or just the rules of exponent? Yeah, all of them. Okay, so for the first three, what I'm gonna ask you to do is write in the conversation just the power. Okay, it's gonna be x to the power of what? Yeah, 5/2 or 2.5. Because what we do is 2 plus 1/2. This is very tempting to do the multiplication, but you don't do it. Okay, next one. The same answer, perfect. And the last one, the easiest, 2. Okay, great. So I see that this is cool, and you see that this is cool, so we can pass that part. So I have extra exercises. So given some of you needs extra exercises, email me. All right, so the relation between x and y. So do you mind writing y in terms of x right now in the conversation? Not the other way around. Y in terms of x. I'm asking about already the second block of exercises. So find the relation between x and y. I see one correct one. I see French keyword. Yes. Well, you got, yeah, okay. So I see the absolute value makes sense. I see that some of you wrote two options. Since we ended up with squares, it is indeed two options that we have. So either y equals 2x, either y equals minus 2x. So this thing is going to be very useful for micro. So managing to express one in terms of the other. Then take derivatives. Okay, so here again you have two options for the relation. And let's pass to the equations. The first one, you can write it straight. X equals 1. So the way we solve it, okay, good. Put a plus right now if you don't know how it was solved, because it's very fast to show and I can show. Okay, great. So what we had is, now I'm gonna get stuck with this power, but just explain. So 4 to the power of x minus 1 is equal to 1. What we're trying to, how we're trying to solve this is we're trying to equal powers of 4. So given, we understand that given we are, I'm out of math? Yeah, I'm out of math. For the step-by-step solutions, email me. And now I'm going to explain the first equation and the previous one of relation between x and y, just in case, okay? So for the equation, what we want is to end up with a framework like that. No, not like that. Something like to the power of to the 4 to the power of x equals 4 to the power of 7. Okay, so given I give you this, you understand that x is equal to 7 because it's an equation, the powers must equal. Okay, so we had something different. We didn't have 4 to the power of something equals to 4 to the power of something. We had 1. But actually, we can create the same framework. So we had 4 to the power of x minus 1, and now it's going to be very ugly again. Sorry. But I'm going to fix it later. X minus 1. Dun, dun. Dun, dun. Okay, that was equal to 1. Great. 1 is what? Every number to the power of 0 is 1. So what we can do is rewrite it as 4 to the power of 0. Alright, and here you have this previous way of writing an equation. You write x minus 1 is equal to 0. X is equal to 1. So that's how we got our first answer. Then let's go back to the relation between x and y, and why we have two options there. Well, first of all, what we're supposed to do is to simplify it. Alright, so we were simplifying it, we ended up with something like x to the power of 2 times y to the power of minus 2 minus 2. Oh, magic. How did that happen now? Okay, equals to the fraction 1 over 4. Okay, how to get here? I hope you got it. Then, what happens? So, we can rewrite it as well as another fraction. So, fraction of x squared y squared equals our previous thing, 1 over 4. Okay, and here we see that no, wrong one. We see that pretty much y squared equals to 4x squared. Right? Okay, that's great. And now out of here, we can just take square roots of both sides, but we have to make sure that we don't lose any negatives, because minus y squared is, well, the square kind of eats the minus, and the square roots, well, I understand how you could get 1, because if you just take square roots of both, you only end up with positives, because square root is something that is always positive. But to properly define the relation between x and y, we have to cover both of the cases. So 2x and y equals minus 2x. Okay, so now I hope this is more or less clear. Given that it's still not clear, send me an email. And then for the last one, so now we have just one equation. And I have the first option, 2 logarithm of 2. This is a good one. You could just stick to logarithm of 4. Yeah, it's a natural logarithm. And how did that happen? This is our standard polynomial. So you've seen ax squared plus bx plus c equals to 1. You've solved it maybe through discriminant, maybe using different theorems. In this case, what made sense? Using a theorem. But, well, anyways. What should we do with it? Should we solve it? Oh, it's a break time. Which is great, because given... Yeah, I agree with all the listed options. Well, I hope the first listed option, log, means natural log. So, let's take our break. Given you solved everything, you can